Lecture number 8, the gas turbine cycles, and we will be doing some solved examples. Example 8.1 of power, power plant technology by Al-Wakil. Find the pressure ratio required by an ideal Brayton cycle to produce a network of 600 BTU per power mass of working fluid of a helium and air, and we are considering the CP at a low temperature. The cycle has got the initial and maximum temperature of 500-degree Rankine and 2500-degree Rankine respectively. Also calculate the optimum pressure ratio for both of the gases. So the question is like we have been given the network, which mean like the turbine work minus the compressor work, which is 600 BTU per pound mass, and we need to find out the pressure ratio, the required pressure ratio for this work done. Then the second part say like we need to find the optimum pressure at which the maximum work done would be possible. So for the let's start the example and example starting from the helium. For helium, the CP is 1.250 and the value of K or gamma is 1.659 as it is monatomic. Then K minus 1 divided by K would be equal to 0.3972. Going to equation number 8.1, and that is 8.1 of 8.11 of Morin and Shapiro. The network is equal to CP, and this one, if you can need to solve this thing, it is written somewhere here. That is actually I've actually derived it using the efficiency formula, which is network would be equal to, sorry, the efficiency would be equal to network divided by the heat supply. And yes, you can solve it later on, and using this one you have to derive the equation, which is equation 8.1 in your book now. Going back to the question, now the network, we have got it. So we have got the network of 600 BTU per pound mass. That is equal to 1.25 into T3 minus T1. In terms of T1, T2, we have written T1 P gamma minus 1 divided by gamma. So, and then obviously we have got the gamma minus 1 or K minus 1 divided by K, that is 0.3972. Solving it, we will be having an equation like this, and this is definitely a polynomial equation. So, for a polynomial equation, you might have got two value, as it is actually having this zone, and that might be another zone as well. So for polynomial equation, when you are solving it, you will get to 2.16 and 26.62. So on these value of pressure ratio, 2.16, you will be having a work done of 600 BTU per pound mass. So yes, that would be somewhere to RP of 2.16 over here, and obviously for a polynomial equation, there's another RP which is 26.162 over here. So this is the pressure ratio at which the work done of 600 BTU per pound mass is given. Now it's like what would be the optimum pressure at which there would be the maximum work done. Let's say for example at it is the polynomial equation, so there would be a maximum slope of the polynomial curve, so and maximum value of the RP. So finding the optimum value of RP, that would be RP, this equation would be used for the optimum value. So our RP optimal, T3 by T1, K by 2, K minus 1, that would be, and you can find the RP value at equal to 7.58. Now putting the RP back into this equation, or this one, so you can find the value of the work done, which would be the maximum work done value, and that is actually 954.8 BTU per pound mass. For the RP, which is equal to 1, or let's say there would be a minimum value of pressure ratio at which the work done would be 0, and also there would be a maximum value of RP in which the work done would be definitely again 0. So the minimum value of the RP in which the work done would be 0 is putting the 1 over here, and obviously 1 minus 1 over here. So that will be multiplied by this one. So you will get the work network as 0. Yes, there would be a maximum work done, sorry, maximum value of pressure ratio, and the maximum value of pressure ratio at which the work done is also 0 is 57.5 in terms of in here in this example. Moving to the next part, which is using the same value, using the same data, um, calculating the value of pressure ratio and the optimal pressure ratio for the air as well. Using CP for air is as 0.24 and the value of K 1.4, and K minus 1 divided by K would be equal to 0.2857. Solving this equation and polynomial equation, the equation polynomial equation does not yield any value. If is in other words, it yield an imaginary value, which mean like the 600 value which is given is a, a kind of a arbitrary value, a kind of an imaginary value, which mean like we cannot have work done of 600 BTU per pound mass for this value of medium, which is air. So now looking at the optimum value, finding the optimum value, it would be 16.72, and putting that 16.72 rp in this equation, equation 8.11, you can find the work done. The maximum work done would be equal to 183.3. So that means like the air can at this condition the air can only produce 183.3 BTU per mass work done, um, and the while the helium can produce 954.8 BTU per pound mass of work done. Now moving towards the another example, example 9.4, example no, 9.4 of Moran and Shapiro. Analyzing the ideal Brayton cycle, it entered the compressor of an ideal air standard Brayton cycle at 100 kilopascal and 300 Kelvin with a volumetric flow rate of 5 cubic meter per second. The compressor pressure ratio is 10. The turbine inlet temperature is 1400 Kelvin. Determine the thermal efficiency of the cycle, the backwork ratio, and the net power developed in kilowatt. So yes, we need to find out the thermal efficiency and the backwork ratio. First thing, we will be solving it for each and every point or each and every state. We need to find out the enthalpy, and once we have got the enthalpy, then we have to put the enthalpies in the equation, and then we can find the thermal efficiency or backwork ratio. So starting from the inlet of the compressor, so inlet of the compressor is 300 Kelvin. Then we have got the isentropic compression from state 1 to 2, where we do not have got any condition given. Then we have got the constant pressure heat addition at 1000 kilopascal and reaching temperature at 1400 Kelvin. Then we have got expansion in a turbine, and expansion in a turbine is isentropic expansion. At 4, again, we do not have got any other any condition given, so we will be finding from state number 3 or either state number 1. And then we have got a constant pressure heat rejection from 4 to 1 back to the temperature at 300 Kelvin. So let's start with the state number 1. So state number 1, if you're looking at state number 1, the temperature of at state number 1 is given. Going towards the A table, we can solve using both the A table and ideal gas equations. So using the A table, which is table number A22 in your book. So let's move to A table at 300 Kelvin. So at 300 Kelvin, the enthalpy is 300.19, and the pressure ratio is 1.3860. So back to the question. So we have got at 300, we have got the enthalpy, which is 300 and 300.19, and the pressure ratio at state 1 is actually 1.386. For the state 2, the condition is isentropic compression and the pressure ratio is given. So the pressure ratio P2 by P1 is equal to 10, and obviously that is also equal to PR2 by PR1, which is over here. So we have already found out PR1 from the A tables. So using that PR1, which is 1.386, multiplied by the pressure ratio, which is given 10, so we can find the PR2, which is 13.86. Once we have got PR pressure ratio at 2, we can go to this A table again and find the enthalpy at state number 2 as well. So looking at table again, we have got the PR at 2 as 13A 13.86. Now moving towards here, we have got 13.50 over here, and then we have got 12.66 and obviously 1438. So there is the our enthalpy somewhere, sorry, our pressure ratio somewhere between them. So we have to interpolate between these two values. So 570 and 500, 580. So by interpolating, when we go to by solving using interpolation, the value of the enthalpy would be equal to 579.9 kilojoule per kg. So we have got now we have solved the state number 1 as well, and now the state number 2. Moving towards the state number 3, that is actually 1400 Kelvin, as the temperature is also given. So let's move back to the A table again. So at 1300, we have got the enthalpy as 1395.97 and the pressure ratio at 330. Sorry, I think that's a 1400. So at 1400, we have got the temperature 1400, we have got the enthalpy as 15.42 and the pressure ratio as 450.5. So now we have got the pressure ratio as well, and we have got the enthalpy as well. So at state number 4, we have got the enthalpy and sorry, state number 3, we have got the enthalpy and entropy and the pressure ratio. Moving back to the question. So solving it, we have got at state number 3, we have got the enthalpy, which is 15.4 kilojoule per kg, and the pressure ratio at 450.8. Now there is an expansion, and expansion is actually isentropic expansion. As the turbine is connected to the compressor, so the pressure ratio at which compressor pressure ratio is 10. So we will be assuming again the pressure ratio of the turbine as 10 as well. Now, if it is not connected, definitely we need to find out, which will be actually discussed in the later lectures. So we have got the pressure ratio from expansion ratio, or the pressure ratio from of the turbine, which is 10. So P4 by P3 would be equal to PR4 by PR3. So we have got the PR3 as 450.5, and the pressure ratio is over here. So pressure ratio P3 by P4 is 10. So P4 by P3 would be equal to 1 over 10. So solving it, so we have got the PR4, which is equal to 45.05. Moving to the A table again, PR 45.05 is somewhere here in between them. So we have got 45.55 and 43.35. So our temperature would be somewhere near to 790. So let's assume like 719, or interpolating, roughly interpolating. So that would be somewhere 780, 89, and the enthalpy would be equal to somewhere some 808, 809. So yes, doing the interpolation, you can solve the enthalpy. Back to the question. So yes, we have got the state number 4. We have got the enthalpy, which is equal to 808.5 kilojoule per kg. Now, once we have got all the enthalpies at each and every point, we have got the uh, formula for the thermal efficiency, which is the turbine work minus the compressor work divided by the heat in. So the turbine work is actually from state number 3 to 4. The compressor work is from state number 1 to 2, and the heat in is actually from 2 to 3. Um, per unit mass already given. So H3 minus H4 minus H2 minus H1 divided by H3 minus H2, putting the value, and you will get the thermal efficiency as 45.7. The back work ratio is the compressor work divided by the turbine work. So the compressor work is actually from 1 to 2, and the turbine is from 3 to 4. Just putting the value, and the back work ratio is 39.6. The net power developed would be equal to the uh, sorry, we have already been given the net power developed would be equal to the turbine work and minus the compressor work. So we have been given the volumetric flow rate, and that is equal to 5 cubic meter per second. So using this 5 cubic meter per second, and then we have got the specific volume. So cubic meter per second, and that is specific volume would is actually cubic meter per kg. So our on this side, that would be equal to kg per second. So yes, using this equation, we can find the mass actually. So the mass would be, no, sorry, this one is already been given. So m dot would be equal to, using the ideal gas equation, PV is equal to mRT, where the R is the universal R. So if you are looking for the specific R, so that would be, you need to divide by the molar mass. So PV would be equal to mRT. Using the same equation actually, so volume would be equal to AV multiplied by P1 and divided by R by m into t. Finding this, using this equation, you can find the mass, which is actually 5.807 kilojoule per kg, and using the formula of this above formula, the work done in a cycle would be equal to 2481 kilowatt. The same question can be solve using the cold air condition or the ideal gas equation. Uh, but yes, the answer would be a little bit different from what actually we have done from the A tables. So that also mean like if you're using the ideal gas equation for different temperatures and different CP values at different temperatures, definitely there will be a little bit change in the answers. Uh, but yes, you can solve it using both of the methods. Thank you very much. I hope like you understand the lecture. If you have got any comments, you can actually write me on my Google Classroom or actually on the YouTube channel. Thank you very much. Have a nice day.